All right, so welcome to the first of the Geometry Labs United seminars. Part of our goal is to connect people from different geometry labs, and I think some schools that don't have geometry labs, so undergraduate research groups, into talking to each other, particularly in this virtual moment where it's harder to connect on our own campuses, to kind of give people a place to connect to each other. Thank you to the lab researchers who went with our, I don't know how many of the announcements that got out, but that went with our date change due to the scholar strike for racial justice. And we also were informed that in Canada, that's happening today and yesterday, as opposed to the US. So Steve Ryan at University of Saskatchewan asked us to share that that was why he is not joining, and we apologize for not realizing the different dates in the US and Canada. And we are going to start off with Jayadev Athreya from the University of Washington, telling us what is mathematics research, and then at the end of the talk, we'll talk a little bit about how we're going to do social and discussions after Jayadev's talk. So.
Claire, thank you for the introduction. Claire, Caleb, Anton, thank you guys for organizing this seminar. It's a real pleasure to see this concept grow. I see some familiar faces in the Zoom, and I see some unfamiliar ones. Hopefully there'll be new friends soon. I want to start, I am at the University of Washington, as Claire mentioned. I want to start by acknowledging that the University of Washington is built on the historic lands of the Duwamish and other Coast Salish people. In today's talk, I'm going to talk about what research is in mathematics, but I'm also going to try and talk a little bit about the stories we tell in mathematics, the stories we tell about ourselves, and what maybe some of our responsibilities are as mathematicians, especially as researchers, to a broader society. I'm going to tell a very kind of quote unquote pure math story, but even in this, I want to try and talk about opportunities to think about issues of larger society. In this moment, I think it's kind of irresponsible to pretend that we don't exist in a larger society. Particularly, thank you again to the organizers for letting me delay the talk a couple of days due to the scholar strike. I urge you to take a look at what that scholar strike meant and what we're trying to educate ourselves about the historic oppression that Black people, Indigenous people, and other folks have faced in the United States and all around the world. And I think that's something we have to pay attention to as mathematicians. So I wanted to start with that. So the title of the talk is, What is Research in Mathematics? And like with any mathematical concept, or in this case, maybe a meta-mathematical concept, I often find it's easiest to start with an example. So I'll start with an attempt at a definition, but I'm not sure how useful that attempt at a definition is. I think the example is really going to be more useful. And again, that example is going to be a story that involves the Illinois Geometry Lab, where many of us here, so Claire, Anton, myself, have all been part of the IGL. Apologies if I'm missing other IGL folks here. And then it's continued in various ways and involves, it's a story that goes back a long way in time. It involves people from all around the world. And so, yeah, maybe I'll just get to it. So an attempt at a definition of mathematics is that it's a precise language for systematic pattern recognition. And maybe it's kind of abstract systematic pattern recognition. We have some abstract pattern and we want to use some sentences to describe the patterns that we see, and mathematics is kind of a language for this. Also in this formulation, maybe it's not so surprising perhaps that mathematics is useful in modeling, because in a lot of modeling, the goal is to abstract certain things, try and generate, use some data, and then try and describe what patterns occur. But once you abstract things, you need kind of a language to describe that abstraction. But like I said, I don't think this definition on its own is terribly useful. I think you really need examples. And I want to start the story, or I want to tell the story of Apollonian circle packings, or at least some part of the story about Apollonian circle packings, which are really absolutely beautiful object. And I want to maybe introduce a new adjective, an adjective at least that was new to me when I encountered it, which is radicand. Radicand is a word that comes from botany. It means taking root on or above the ground, rooting from the stem like the trumpet creeper and the ivy. It's something that can place roots wherever it goes, and it can kind of grow from many different places. So it challenges the concept of a single root. It's something that has multiple roots, multiple strands that kind of intertwine. And for me, a lot of mathematics is like this. And so here's this concept was introduced by a theorist named Nicholas Bourriat. He's an art critic, actually. And his phrase, to be erratic, it means setting one's roots in motion, staging them in heterogeneous contexts and formats, denying them the power to completely define one's identity, translating ideas, transcoding images, transplanting behaviors, exchanging rather than imposing. And to me, this is a lovely way of sort of encapsulating a lot of the things about mathematical collaboration. You come from a certain place, you come from a certain personal background, but that doesn't completely define you. Of course, it does change your circumstance and so on, but it allows you to kind of explore. And then I love the idea of transplanting behaviors and exchanging rather than imposing. And I think this is something that especially research in mathematics, collaborative research, and especially research in the context of geometry labs is all about exchange. If you think about a class, a traditional mathematics classroom is something, okay, well, here's what you're going to have to do, and here are the things you have to do. There's a lot of imposition, which can be okay, but in a research setting, it's all about the exchange of ideas. And so this is a phrase that I've really grown to kind of love. Okay, so I promised lots of pictures. Here are some pictures. I find these pictures quite beautiful. You've probably seen some of these if you look at various galleries of mathematical images. These are pictures of Apollonian circle packings. I'm going to let the numbers in this one at the bottom right-hand corner remain a mystery for just a brief moment. I'll tell you what they are in a bit. You can think about that a little bit. The colors here are chosen to make things pretty. And here is the starting point of this story. It goes back a couple of thousand years. There was a mathematician named Apollonius of Perga, or at least this theorem is attributed to Apollonius of Perga. And it says for any three mutually tangent circles, there are exactly two circles tangent to all three. Now, a couple of remarks. Apollonius of Perga is often thought of as Greek. Perga is in Turkey, modern day Turkey. This is actually a common thread that's true about a lot of mathematicians that we attribute as Greek. They're from places across the Mediterranean and up through a much bigger cultural and sort of geographic spread. For example, Eratosthenes, you may have heard of the sieve of Eratosthenes to try and refine the integers to get prime numbers. You cancel out the multiples of 2, the multiples of 3, the multiples of 5, the multiples, and so on. And then what you're left with is this prime numbers. That's called the sieve of Eratosthenes. Again, Eratosthenes is thought of as Greek. Eratosthenes was from North Africa. It would be anachronistic to put a modern nation state on it, but Eratosthenes was an African mathematician. So it's also important to remember as you see these stories how they're filtered in, how these different histories are filtered in and can be narrowed sometimes, which is why it's also important to think about this idea of these multiple roots and kind of a Radicand story. And of course, the story that we have is only the story that survived to us. Who knows how many people have thought about these things over the years, and that even they wrote them down, but we haven't sort of survived and we haven't gotten all the things that are recorded. So the caveat whenever I attribute something to someone is, well, this is what was written down and this is what we have, but it doesn't mean that they're the only person who's ever thought about this. Okay, so here's the picture of the theorem. The black circles are three mutually tangent circles, just in the Euclidean plane. And there are two circles mutually tangent to all three. So I have to touch all three circles. So the little red circle and the big red circle. So again, I find like that this illustration of the theorem is much more useful than, I understand the statement of the theorem by this picture. Are there questions about the statement of Apollonius's theorem? This is the starting point for the math discussion we're going to have. Okay, by the way, feel free to ask questions at any point via the chat, via your voice, via the raise hand function. I'm always happy to be interrupted. Okay, now here's a picture of the question that my colleagues at Illinois and I tried to answer. This is a project that I worked on a few years ago that was also part of an IGL, Illinois Geometry Lab project. So here is a picture of an Apollonian circle packing. That blue circle is this kind of outer circle. So as Apollonian circle packing happens, when you start continuing to do this process. You start with any triple of circles in the packing and you draw the next two circles. So for instance, you might draw a little circle right here. Well, it's supposed to be a circle that's tangent to the green and the two reds. Or you might draw a little circle here that's tangent to the green, the blue, and the red. And you keep doing this, and you get this kind of fractal picture. So maybe another one right here. That keeps repeating. And now what I'm going to do is I'm going to designate my favorite circle in the packing. In this case, it's this outer blue circle. I'm going to draw a concentric circle to it. And then I'm going to ask how much of that concentric circle passes through circles in the packing that are tangent to my original blue circle. Okay, so in this case, the circles that are tangent to the original blue circle, the ones that I've drawn, this one's tangent. I'll put little check marks on them. Right, these are the ones that are tangent to my original circle. None of the other ones are. And I'm asking how much of this blue circle, thin blue circle, passes through them. And then I'm going to ask a kind of a limiting question. As this dotted blue circle converges to this outer blue circle, does this quantity have a limit? So here's another, I'm going to show you lots of pictures. This is a picture that I really like because it was drawn by my friend Vinayak Verma, who's a very talented illustrator, for an article I wrote for a children's science magazine. And I just love the kind of watercolor nature of this picture. So I wanted to share that as well. So, okay, so maybe before I, let me also state some other prior questions about Apollonian circle packings. How many circles will we get? How many of at least a fixed size? How do the sizes of the circles relate? So you start with a concept, you start with a theorem, and then you start to generate questions from a process the theorem guarantees you can happen. This is one of the big ways that research in math happens. You start with something that you kind of know, you do something to it, and then you generate more questions. So here's a beautiful result, another beautiful result. The bend of a circle, also called sometimes the curvature, is 1 over the radius. So the smaller the circle, the larger the bend. So now going back to that original picture, the numbers in that Apollonian circle packing were the bends of the circles. The numbers got bigger as the circles got smaller. So we can just go back for a second to that picture. So these numbers in there are the bends of the circle. So you can see as the circles get smaller, the bends get bigger. And notice in this case, all the bends are integers, which is a really interesting phenomenon that happens. But you can't find circles with infinitely many bends. Okay, now there's a picture of a horse. Well, I don't have kids, but I feel like that shouldn't prevent me from making dad jokes. So here's a joke. Don't put Descartes before the horse. So there was the horse, so I put the horse before Descartes. René Descartes, of course, was a French philosopher and mathematician. And he was corresponding. So as always, scientists, mathematicians, philosophers were always trying to get funding to do their work. And part of that funding was to correspond with people who could potentially fund your work about things they were interested in. So Princess Elizabeth of Hanover was very interested in mathematics and presumably did some mathematics of her own, though we don't necessarily have records of that beyond these letters. And Descartes, in a letter to Princess Elizabeth, wrote down this beautiful formula. Let A, B, C, and D be the bends of mutually tangent circles. Then they have this beautiful formula. If you add up the squares of the bends and you multiply by 2, that's the same as adding up all the bends and squaring it. So this is Descartes' theorem about the bends of circles. And Descartes' theorem, so there's a long tradition in, at least there was a long tradition in mathematics in India that you would write, and across the Arab world as well, that oftentimes you would try and remember theorems or try and encode theorems in couplets or poems. This is much more modern. This is Frederick Soddy, who was a Nobel Prize winner in chemistry, got this poem. This is only the first verse, by the way, published in Nature. I guess if you're a Nobel Prize winner, you get your poems published in Nature as well. And the poem, and this poem is really quite lovely. 4 circles to the kissing come. The smaller are the benter. the bend is just the inverse of the distance from the center. Though their intrigue left Euclid dumb, there's now no need for rule of thumb. Since zero bends a dead straight line, and concave bends have minus sign, the sum of the squares of all four bends is half the square of their sum. So that's a summary of Descartes' theorem about the curvatures of Apollonian circle packings, which I quite love. So back to this question, are there packings with all integer bends? And there's an example of a packing with all integer bends. It's not so hard to see that that equation for the bends is, if you start with A, B, C, and D are integers, or A, B, C are integers, D might be an integer, right? This equation relating the bends has the potential, is defined over the integers. It's defined over Q. So you're kind of in good shape to generate integer bends. So here's some recent developments about Apollonian circle packings. The number of circles with radius at least, say, 1 over r grows like a power of r as r grows. That was proved by Alex Kontorovich and He-Oh. Alex is a friend of mine who now teaches at Rutgers, family origins in Russia. He-Oh is from Korea originally. And that power of r was actually guessed earlier. I unfortunately don't have the citation with me right now, but they proved that power worked. But that power was guessed using computational techniques. So there's a lot of experiment that's gone into this as well. All sufficiently large numbers are integers are represented as bends in an integer packing as long as they satisfy certain divisibility conditions. This is Elena Fuchs, who's now at UC Davis. Again, her family is originally from Russia. Elena did this in collaboration. Some of the work was done in collaboration with Kat Sandin, who was an undergrad at Princeton. So undergraduates have been involved in this story for a long time. And people contributing to the story include mathematicians from South Africa, Korea, India, France, the US, Canada, all over the world. Again, this kind of big story. And now I'm going to tell a story about a collaboration between me, an American mathematician with roots in India, and a couple of Romanian mathematicians. And so here again is the question. You start with your favorite circle. Now this time it's this thick blue circle. Oops, what happened? Sorry, let's play that again. This thick blue circle, you take a concentric circle, which is dashed in blue, that passes through circles tangent to the original one, in which case here I've colored all of them red, and you ask how much of this dashed blue circle is red. So this is a zoom in to a tiny piece of it. This is a project I studied with Cristian Cobelli and Alexander Zaharescu. And we proved that as the circle converges to the thick blue circle, the fraction of the dotted line that is red approaches not 1. You might suspect that it gets to 1 because there's kind of grains of sand kind of fill it up. It's not 1, it's about 95%. That 95% is actually 3 over pi. It's not just 95, it's 3 over pi. And this was done by myself, Cristian Cobelli, and Alexander Zaharescu. Alexander and I were colleagues at the University of Illinois. Cristian was a colleague of Alexander's at the Institute Simon Silo in Bucharest. Cristian and I still have never met in person. So you can collaborate with people, it's a good lesson for the pandemic, without ever meeting in person. And again, another thing I want to emphasize is that math is kind of very connected. Our proof uses hyperbolic geometry, number theory, and complex analysis in surprising ways. What's kind of very fun is you can guess this limit, this 3 over pi, quite easily with just open source software, CoCalc or Sage Math. It's not so hard to generate an Apollonian circle packing and guess what this limit ought to be. So optimal rate of convergence, if you want to understand how fast it's converging to 3 over pi, that's actually equivalent to the Riemann hypothesis, which is, of course, a very famous open problem and would get you $1 million if you solved it. If you do the numerics behind our problem, you do see the optimal rate popping up. I'll mention that the IGL project that we worked on studied the rate of convergence in a circle packing, but it also generalized to what were called Soddy sphere packing, which is going up a dimension. When we went up a dimension, sorry, this was an IGL project with Jason Hempstead. Jason is now finishing his PhD in physics at the University of Washington. We actually ended up moving to Washington at the same time. Donnie Wu, and I'm blanking on the third person's name. My apologies. I had it. I don't have my notes here right with me. But they wrote a paper that got published in the Rose-Hulman Undergraduate Journal describing their work. There's also more questions related to this, but really these slides are more or less an excuse to show beautiful pictures of these things called Schmidt arrangements, which are kind of generalizations of some of these circle packings. And these are pictures due to Kate Stang, who's a mathematician at the University of Colorado. Just wanted to sort of finish off by showing you these amazing pictures and think about, maybe there are some questions. You can look at Kate's website and figure out, how to define these Schmidt arrangements, and what are some of the questions you could ask about these Schmidt arrangements. Now, of course, I'm preaching to the choir here. If you're interested in these kinds of questions, if you're interested in the kind of stories I tell, of course, join a lab. But maybe the better thing to say now is tell your friends to join a lab. The point is anyone is welcome to these things. These labs are centered around experiment, exploration, and collaboration. And you don't need to know an enormous amount of math to start doing research in math. I often find, and this has been true throughout my career, the best way for me to learn a new piece of math is to try and start doing a research project on something related to it. It helps motivate me, it helps keep me excited. So if you feel like you don't know something, I don't really know what a scheme is. That's something that's very important in math. But I keep trying to learn some algebraic geometry by doing research, and maybe one day I will know what a scheme is. Similarly, if you hear a word that you don't know, do a research project on something related to it. You'll learn something about it. So I think that's a good place for me to stop.
I'm unmuting and clapping. Yeah, so I think, Jayadev, we have maybe like 1 minute for a question, like one question, and then you need to run. Yeah, because again, thanks to the organizers for being so flexible. Because of time zone confusion, I thought I was giving a talk at Penn State at 3:30 this afternoon my time. Of course, it's 3:30 Eastern time, which is in about 7 minutes. But I'd be happy to stick around for a minute or two for any questions. Also, feel free to email me if you have questions. I know sometimes it's not easy to come up with questions in the spur of the moment. Send me an email if any of this stuff excited you or intrigued you. I'll let people have a minute to either unmute or type in the chat a question, and then we'll talk about logistics, because Jayadev's running, but the rest of us aren't, unless you have a class.
Yeah, I think my keys are in my purse. So, okay. So part of what we want to do is let people kind of talk. This isn't a huge group. Yes, so thank you, Jayadev, also for kicking us off. And so we want to let people kind of talk. We are going to, I believe, have a option for undergrads who only want to talk to other undergrads. I believe we have a link for that. Although it's just small enough, we could probably just throw people in breakout rooms. And then, I don't know, faculty want to talk to each other, although, I don't know, maybe they're disappearing, logging out. Or if people just want to hang out here and not jump into undergrad and faculty things. We did want undergrads to have an option to kind of talk to each other if they don't want to talk with faculty around. Or people can just unmute here. Ask other questions. We looking at the list, I do not believe we have any other circle packing experts, but we can answer other questions. I did set up a room, Anton.